Wonderful. Thank you to Quentin and the other organizers for the invitation and the introduction too. All of this is joint work with Eitan Levin, who was there, and really it's his work that I'm fortunate to be able to present. That's good. And so this talk is inspired by a phenomenon that arises quite commonly in mathematics, where we assert inequalities or make other kinds of statements that hold for all dimensions. I'll give some examples. And the idea is that we want to develop optimization-based methods to try and solve or produce bounds in these kinds of problems. So what do I mean by any-dimensional problems? Or problems that arise in sequences. I have a few examples on the slide. The first one is what we'll call the monomial means problem. Sorry, I'm not able to maneuver this very easily. I might just use my finger. If you take the expression right at the top, it's the empirical average of the kth power of a bunch of points xi, and based on the formula for mk, we can write down this polynomial Qn that involves the fourth, third, first, and second of these monomial means. Qn is a polynomial in X. And what's interesting about Qn is that it's somehow evidently defined for all n, right, just in the way it's written. And the question is it the case that Qn is non-negative for x's in the box, but for all n, not just for a fixed n? If it were a fixed n problem, this is a finite dimensional polynomial optimization problem. You could throw the kitchen sink of optimization, the toolkit, everything that we have at that problem. But here we're interested in checking this inequality for all n. Okay? The growing sequence of growing dimensional problems. Another example, these are symmetric functions, the same kind of expression as we have up top, except that you don't normalize here. And here we have a different Qn involving S6, S4, the constant term. Again, an expression that's defined for all n. And the question here is this Qn non-negative over the Euclidean sphere, but again for all n? Yes? To the limit, I want this to be non-negative for all natural numbers n. Well, the limit needs to be well defined, but if it is, yes. But in what we will discuss formally, the limit, yes. You're right, good question. This is an example of a Newton identity, and it turns out that the answer is yes. The first one too, the answer is yes. A third example of this kind of phenomenon is one arising in extremal combinatorics. Here you have graphs h and g, and this expression t of h comma g is the fraction of mappings from the vertices on h to the vertices of g that are homomorphisms. Okay? So roughly speaking and formally, the number of copies, if you will, of h inside g. And the question we're interested in, potentially, is does this inequality hold for all possible graphs, meaning for all possible g's and any number of nodes? Again, for a fixed number of nodes, n, I can take this expression, translate it into a finite dimensional optimization problem, in fact, a polynomial optimization problem, and apply my usual tools. But I want to be able to answer this question for graphs of all sizes. Okay, and this says that the normalized number of copies of triangles plus the number of edges must be bigger than or equal to 2 times the number of disjoint edges in G, right? And this should be true for all G. The answer again here is yes. It's a theorem called Goodman's theorem. But these sorts of phenomena arise commonly in mathematics, where we make assertions or state inequalities that hold for all n. And these kinds of questions are the focus of this talk. So what we're imagining is that we're given a sequence of polynomial minimization problems with optimal values un, and we're interested in producing bounds, in particular lower bounds, on all of them simultaneously, or equivalently, a lower bound on what we'll call u infinity, which is the infimum of all of these expressions. So this sort of speaks to your point about the limit. We'll always, when I talk optimization in this talk, I'll always imagine minimization. So lower bounds are the question of interest, really. So we have a sequence of minimization problems, and we want to produce a bound on all of the optimal values simultaneously. Okay. Lots of challenges. In general, bounding just one of the UNs is not enough, because it could be the case that as you take larger and larger n, the optimal values keep decreasing. So just picking one n and producing a bound is usually not good enough. It's not good enough in each of the three problems I mentioned previously, and it will not in general be good enough. Another challenge is that the sequence of problems that's indexed by n has growing dimensionality. So they're growing in size. And in general, for such any-dimensional problems, checking whether u infinity, this expression, is not negative, for example, is undecidable. So if you go back to the previous slide, this problem with homomorphisms, if I plug in a general expression involving these t's, this is undecidable. Okay? So all of these are challenges to being able to try and address this general question. But what we'll aim at is to produce lower bounds on u infinity using finite-sized polynomial optimization problems. That is the goal for today. This doesn't preclude, or this doesn't contradict undecidability in any fashion. We're just interested in producing lower bounds in u infinity. It is still in general the case that you may need to do an unbounded amount of work to check that u infinity is not negative. So this is fine. We're just interested for now in producing lower bounds in u infinity. And the key ideas that will play a role is this phenomenon that's sort of recently discovered in the representation theory and algebraic topology literature called representation stability. And surprisingly to us, a link with Finetti's theorem from probability. Okay, so these are the two key ideas that will play a role in achieving this agenda. Once you have this, you can then apply, again, these are minimization problems, so you can then apply the usual toolkit of convex relaxations, for example, based on sums of squares or other techniques, to produce further lower bounds on these finite-sized pops to then get a lower bound on u infinity. So that's always possible. I'll touch upon this point very briefly, but much of this talk will be focused on these two ideas with a view to producing finite-sized pops that lower bound u infinity. Okay? Once we have this, we have tools already. Yes?
Yes, so you just want a lower bound, but you don't want a sequence of lower bound that would converge to
we will in fact be producing a sequence of lower bounds that will converge to u infinity. Yes. But yeah, one would be nice, and then we can do more. But yes, we will in fact produce a sequence. Yes. So, and it's the usual agenda where you need to do more work to get better answers. Okay. So much of this talk will actually be focused on one case study that has all of the key ingredients. And it's about over half the talk. And then we'll go through how we can extract the key insights from this case study to formulating how do you even describe any dimensional pops in general. You don't want to be writing down an infinite specification for an infinite sequence of problems. How do you finitely specify any dimensional pops? How do we generalize Finetti's theorem? It turns out that classic Finetti's theorem, the original theorem, is what's relevant in this case study, but we end up needing to generalize it to be able to apply it more broadly. And I'll very briefly at the end touch on the structure of semidefinite programming lower bounds that you could apply to our framework. But much of the talk is the first bullet point and then the next couple. Okay, so let's go back to our monomial means problem. I'm going to do it in higher dimensions than the statement I had right at the beginning of this talk. We will fix m exponent vectors, alpha 1 through alpha m, a semi-algebraic subset theta in Rd, and a polynomial f in m variables. And I'm interested in the following sequence of polynomial optimization problems over d cross n. D because each of these variables lives in Rd, and then there are n of them. And the objective function is to minimize this polynomial applied to the empirical averages of these monomial means. Okay? A couple of observations first. If I take the nth problem, and I take a feasible point for the nth problem, meaning x1 through xn are all points that belong to theta, and I create k copies, if each of x1 through xn, I get a feasible point for the knth problem. And this is really important because it speaks to how these problems are related across dimension. If you have an arbitrary sequence of polynomial optimization problems or any other optimization problems, you have no hope of bounding any limiting sort of optimal value. That's like producing bounds on an arbitrary sequence of numbers. But this speaks to the idea that these problems in general are related across dimension, and we'll speak to this point more precisely as we go later on. But in this example, this is how they're related across dimension. And what we have as a consequence of this relation is that for all n and k, we have the sequence of inequalities. And this tells you much more precisely that if I produce a lower bound on the nth problem, that's in general not enough to produce a lower bound on u infinity, which is the infimum of all of the u's. Good. So this observation is useful to keep in mind. More broadly, though, the nth problem, the thing we just had here, entails optimization over measures of that form. There's delta functions, the xi's, and 1 over m, just empirical measures. So that suggests a formulation for the limiting problem, which can be viewed this way. So let's go through this slowly. The limiting problem is a polynomial optimization problem over moments. And these moments arise from a measure that's a probability measure on theta. Okay? And the goal is to take this pop over moments and try and derive a finite dimensional pop to lower bound u infinity. Okay? So this is more concretely the question when we, for the monomial means problem. Okay? Whoops. Bit of contrast with prior work. So let's imagine f is a degree 1 polynomial, so a linear function, linear affine function. Then instead of a polynomial optimization problem over moments, you have a linear program over moments. And it turns out, and this is classically known, that this is simply a finite dimensional pop. So if f has degree 1, we get back to a usual finite dimensional pop, and we're done. There's nothing more to be done with respect to our agenda. The case where d equals 1, so d, if you recall, is the dimension in which the semi-algebraic subset lives. So if d equals 1, these random variables are all dimension 1, and theta is an interval. This case was studied quite recently and completely in this paper. And so this is another case that's been completely established and resolved. But we want to understand this problem more generally. Yes?
If f is convex, you should also work with the classical. You have an SDP for the moment that says that mu belongs to p of theta.
That is right.
And then you have instead of having an SDP, you have a conic problem with a non-linear term, but convex, right?
I will have to think, but if f is convex, it's a polynomial but convex. Or are you?
So you have a sort of.
It's an interesting.
Semi-definite present.
Yeah, but the cost is not linear like in SDP, but it's convex.
But
Correct. That's right.
But
That should work, no?
Well, I'm not sure because the constraints are in general. I mean, these are not. The dependence on mu is through moments of mu, and so.
You have a spectrohedron with a convex cost.
I think if it's f is polynomial with a yeah, let's talk offline. But that's intriguing. I'm in general interested in trying to understand when this is sort of directly finitely solved using classical methods. But these are two certain observations one can make. Okay, but we want to do this for a general d, and d again, recall, is the dimension of theta. Okay. So again, this is our problem. We have a bunch of exponents in d dimensions, semi-algebraic theta, and an m-variate polynomial f, and this is the limiting problem that we wish to solve. If f is a monomial with exponent beta, then I'm going to go through a sequence of reductions to really understand what's going on, and it's this insight that will help us. So if it's a monomial, I can write f in this way. The product remains the same here, so let's ignore that, and let's just focus on this bit. What I've done is that there are beta I copies of this. So I've just written a product measure here, and these are independent random variables, x1 through x beta I. And then I can do the same thing for this expression multiplied by itself m times, right? Or not m times, but as I ranges from 1 through n. This is for I equals 1 all the way till I equals m. And I have a product measure here. And the x have double indices now, but the idea is that these are all random variables, and I'm taking the expectation with respect to this giant product measure. But the upshot of this logic is that when f is a monomial, we have identified a monomial p, and d times degree of f many variables, such that this is true. That into f, when I plug in these moments, that's equal to taking the expectation with respect to a product measure of p. And f, being a monomial, yields a monomial p. So we can take this basic observation, and by linearity, simply assert that when f is a more general polynomial, we have the same expression holding for a polynomial p in d times degree of f many variables, with the number of terms in p being the same as the number of terms in f. Okay? So what we can conclude, based on this observation, is that this original problem that we had here can be written now as an optimization problem, where the objective is the expectation of a polynomial with respect to a measure nu, where nu is of this product form. Good. The next step, so we've really used independence here. That's sort of all we've used in this deduction. The next step is where d Finetti comes in. Again, this is simply an assertion of what we've done so far. The alphas, theta, f are fixed. The top line is the original problem. The second line is what we've concluded so far. And the first thing you can say when you have an objective of this type is to recognize that that objective is linear in that measure nu. So you can take the convex hull of the constraint set. And when you see convex hulls of product measures, you think d Finetti. And what you get is the second line by d Finetti's theorem, which is the decision variable now is not just a single measure, but a sequence of measures, nu I. Nu I is a probability measure on theta I, that is theta product with itself I times, exchangeable, and it extends as a sequence. So this is an infinite sequence of measures, but this is where d Finetti applies. Convex hull of product measures is given by exchangeable measures that extend infinitely. Good. This is all so far still exact, right? And step 3 is where we'll get to a lower bound. So again, the first bit is our original problem and the reformulation we've gotten to so far using the Finetti independence. And what you can simply do now is rather than taking an infinite sequence of measures, just truncate it at some n. The n needs to be sufficiently big, bigger than the degree of f, because that's the index you use here. But then the constraints are the same, and you've just truncated right here. And it's evident, based on this expression, that Vn is a lower bound on U infinity. And you have, this was sort of assert, I haven't proven that this is a polynomial optimization problem yet, but we have a sequence of lower bounds that as n grows large will yield a limit that's actually equal to U infinity. It's the sequence from below. And the last step, which is where we need to obtain a finite dimensional polynomial optimization problem, goes as follows. This is our original formulation. This is the lower bound we've obtained so far. These are the constraints, an n-length moment sequence. And P is a polynomial in D times degree of f many variables. One thing you can do is to view P as a polynomial in D times n variables, and recall is bigger than or equal to the degree of f. And simply get rid of this moment sequence, and just imagine that nu is a measure on theta n, probability measure on theta n, that's exchangeable. So I can just imagine P has all these extra variables that it does not depend on, and write this down. Questions? So this is what our lower bound is so far on U infinity.
But the constraint of exchangeable is that easy to implement?
Well, this is not quite a finite-sized pop yet. There's one last observation to get to that, but yes. So this is what we have. But as was observed, this is not quite a finite-sized pop. We need to deal with this exchangeability, a constraint. And what we can do is that since nu is an exchangeable measure, we can symmetrize P, because an objective function is bilinear in nu and in P. P now viewed as a polynomial in D times n variables. You can take the symmetrization, and the lower bound becomes this. At the previous line, we had this expression with exchangeability in the constraint and P viewed as a polynomial of D times n variables. But once you put a symmetrization here, you can get rid of the exchangeability. So this is an optimization problem where you take the expectation of a symmetric polynomial over all probability measures on theta n, and this measure mu you can view as taking convex hulls of delta functions on theta n, and this is simply a polynomial optimization problem, a classic finite-sized polynomial optimization problem. We didn't really use that theta was semi-algebraic all the way through, except here, to assert that this is a pop. Right now it matters that theta n is given by polynomial inequalities. So we have a finite-sized pop that lower bounds U infinity. Good. Let's do a quick recap. This was our original problem. I've stated the UNs, not the U infinity, just each sequence of problem. Each problem in the sequence. We have a lower bound on U infinity in 4 stages. The first step used independence, so we had product measures. Step 2 took convex hulls of those product measures and used Finetti to state things in terms of sequences of exchangeable measures, an infinite sequence of exchangeable measures. Truncate to finite sequences. Up to step 2, up to and including step 2, we had an exact reformulation of U infinity. Step 3 is where we start producing lower bounds. So you truncate to finite sequences. And finally, you go through the symmetrization step to actually produce a finite dimensional pop. Yes.
The fact that you have a symmetric polynomial, does it simplify, like for, of course you integrate with respect to a measure, but if it would be a polynomial optimization
Classically.
symmetric, there are some results on the half-degree principle, these kind of things, right?
Substantial simplifications. In fact, I'm going to allude to it very briefly in this talk at the end, but one sense in which there is a simplification is certainly when you use STP relaxations, you can get reductions in size of those STP relaxations. More interestingly, when you take the sequence Vn of lower bounds given in terms of these symmetric polynomials, there's a relation between those STPs across n. And so all of those are things you can say for this invariant. But the fact that this is an invariant pop is significant and interesting. But for now, we've achieved our larger agenda of producing a finite-sized pop. Good. So how do we generalize this? We went through this agenda for monomial means. A lot went into it. The very first thing is, how do you evenly finitely parameterize or state sequences of polynomial optimization problems? If you go back to the previous slide, this is a sequence of problems, but somehow in its formulation is evidently instantiatable for each n. You give me an n, and I can tell you what the actual problem is. But there's only somehow finitely many parameters that go into the description of this problem. So what's the underlying principle there? How do we apply Finetti more generally? And it turns out that the key insight in this entire exercise is that you can take a sequence of polynomial optimization problems, and in these 4 steps that we had, the right abstraction is the second step. The second step, if you recall, was post the application of Finetti, which is that you take these any-dimensional pops, the sequences of pops, and you can reformulate the limiting optimal value as an optimization problem over sequences of measures. You take the expectation of a polynomial p for one of these measures in the sequence, with respect to one of these measures in the sequence, the same constraints that we had before. This is the right abstraction for an appropriate notion of projects. So if you're able to be flexible about what projects means, you can accommodate lots of classes of sequences of pops into this formalism. But it requires, of course, being able to answer the first 2 questions. Which classes of sequences of pops? How do you finitely describe them? But also, how do you apply Finetti more generally? Because this was the consequence of having applied Finetti in the illustration we just saw. So this is what we need to be able to go through. Okay, so how do we formulate any-dimensional pops? That'll be the focus of the next few slides. I'm going to abstract away from the example that we just saw. We'll write down a sequence of polynomial optimization problems where the optimal values are un. These are polynomial optimization problems over a sequence of vector spaces, Vn. The objective polynomial is a polynomial at Vn, and omega n is a semi-algebraic subset of Vn. This is what we mean by a general sequence. Any sequence is of this form, but of course we need some relation of the problems across different dimensions here. The one thing you'll notice, both in the monomial means problem that we went through in detail over the past few slides, but also early on, right at the beginning of the talk, is that each problem, if you focus on just the nth problem, it's invariant under an appropriate action of the permutation group. So with monomial means, if you take the nth problem and you swap the xi's, the objective and the constraints remain invariant. This was also true of the graph homomorphism problem I'd stated earlier. So if the sequence of permutation groups acting in an appropriate way on a sequence of vector spaces, and the nth problem is invariant under this action. Perhaps more subtly, these problems are related across dimension in different ways. I alluded to this with the monomial means problem, where you take n points, duplicate them, and you get a feasible point for a larger problem. And it turns out that that's one of two interesting ways that we've studied in which problems can be related across dimension. And this is really key to being able to formally state any-dimensional pops. So again, we have this general formalism, and we'll try and abstract out these common features. As with the monomial means problem, several problems are related by what we call the duplication map. Take a feasible point for the nth problem, duplicate each of the variables k times, and you get a feasible point for the knth problem. And both for the monomial means problem as well as for graph homomorphisms, it turns out that if you take a feasible point, duplicate, the objective values are the same, and when you apply the duplication to the nth feasible set, you live inside the knth feasible set. This is one way in which these problems could be related across dimension. The examples of monomial means and homomorphism densities, you take an adjacency matrix of your graph on n nodes, and you product it with a k-clique, and you get, as it turns out in that problem, a feasible point for the knth problem. So duplication can take a few different forms, but the moral idea is just really copying it k times. So in all such problems where the different elements of the sequence are related by duplication, you have that the optimal values satisfy this relation, just evidently. It turns out that when you take sequences of polynomials that are bounded degree and invariant, and that satisfy this duplication relation, that such sequences form a finite dimensional vector space. And this is a consequence of this phenomenon called representation stability, where when you have a sequence of groups acting on a sequence of vector spaces, and the sequence of invariant spaces associated with the sequence of actions stabilizes in dimension. So this is a phenomenon that was recently discovered, recently meaning I think circa 2010 to 2012, and it's been explored in the pure math literature since then. And this tells you that if you have any dimensional pops where the objective satisfies this relation across dimensions, you can finitely specify it. Because you have a finite dimensional vector space, you can write down a basis for that vector space, and you're done.
And that holds for many groups?
This holds for, so in this talk, I'll only be talking about the sequence of permutation groups. This phenomenon holds for all the classic while groups, so permutations, sign permutations, and so on. In work Eitan's done, we've looked at representation stability in the context of Lie group as well. So Lie groups, so when you have orthogonal invariance also. I don't think representation stability, as far as we know, has been fully established in that context. And there are some challenges there. But certainly this phenomenon goes through for symmetric and things in the neighborhood, all the classic while groups. So this holds. So, and you can imagine a similar sort of situation with the sequence of constraints too. But you can finitely specify any dimensional pops if they're related across dimension via duplication, and they exhibit these kinds of relations, and they're invariant in bounded degree. Good. Some problems, some any-dimensional problems, are related across dimensions simply by zero padding. So you take a feasible point for the nth problem, pad zeros, and then you get a feasible point for a larger nth problem. So symmetric functions, which we stated early on, if you go from homomorphism densities to homomorphism numbers, where you append a graph with some extra isolated vertices, these are all examples of zero padding. And if you have the same kind of relation across dimensions with zero padding, and for the constraint sets, the optimal values now satisfy this sequence of inequalities as n grows. And again, representation stability tells you that bounded degree and invariant polynomials satisfying this relation form a finite dimensional vector space. So again, you can specify problems that are related across dimension by zero padding in a finitely parameterized way. Right, so this is really key. I can actually tell you in a finitely described way what an infinite sequence of problems is. Yes?
Is there an easy to understand? Is it easy to figure out what this finite dimensional?
Yes, in fact, I mean, computing a basis for it is sort of fully algorithmic, and so there's code to do this. It produces a basis, and then to present your problem, you just have to give the coefficients in that basis.
It's not the finite dimension is not too large, depending on.
It depends on the sequence of vector spaces and so forth. But yeah, you can get to dimension 1 or 2. You can get to crazy large dimensions too. If you take just the sequence of Rn, sequence of vector space Rn, and you just take the standard action of the permutation group, the sequence of invariants is one-dimensional. So you can get low-dimensional things, but you can also get very complicated high-dimensional objects. But always finite, finitely parameterized. You should think, if you have a finite dimensional polynomial optimization problem, but the degrees are high, in general, of course, you're going to need a lot of numbers to describe them too, right? So it's a function of what you want also. Yeah. So few things. Representation stability tells you that in both cases you can specify these problems finitely, but also that the optimal values are decreasing in two different interesting ways, but it's never going to be enough to simply stop at some finite n and produce a lower bound. You really do need to worry about the limit. Okay, so that's how you describe problems. How do we turn this crank of de Finetti? Again, let's revisit the monomial means problem. This was that prescription. Using de Finetti, we had this reformulation. We identified a polynomial p and an index degree of f such that the limiting optimal value could be written in this way. This was after applying de Finetti. What if instead of monomial means you had graph homomorphism densities where you needed to verify inequalities involving homomorphism densities for graphs of all sizes? It turns out that exactly the same reformulation goes through, but with projects replaced by taking induced subgraphs. It seems believable that this is a natural analog of projects when you look at graphs, but the underlying reason why this is true is due to a generalization of a two-dimensional or higher dimensional generalization of de Finetti due to Alice and Hoover, what they call exchangeable arrays. So it's that technique that you'd apply to do this. Okay, this problem is related across dimension by duplication. So are the homomorphism density problems, right? So let's make a more general statement for problems related across dimension by duplication. So if you have an any-dimensional pop with a sequence of optimal values un, and the sequence of pops is related across dimension by duplication, it turns out that you can write down a characterization of the limiting optimal value as a problem over sequences of measures where there exists some polynomial p, an index L for the sequence of measures, and a notion of projects given by the adjoint of the zero padding map. So if the original problem is related across dimension by duplication, projects is given in terms of zero padding. So that suggests a kind of pairing or duality between those things. And truncating this formalism yields lower bounds Vn via finite dimensional pops. Okay? So the u's are related in this way, approaching u infinity, and the v's, the lower bounds that you get by truncation, are related in this way, n to n plus 1 to v infinity, and those limiting values are equal. These are finite-sized pops, and you get a bound on the rate. Yes?
So what you seem to say that when you have a sequence of growing dimension problem, the key to have some insight is that feasible solution of one, there is a way to complete it to make it a solution of...
Precisely. They need to be related across dimension in an interesting way. Yes. That's really key. That's right. And then you can turn this crank of de Finetti to get this. And the proof here really, is based on a generalization of Finetti, a classic Finetti, that includes the Aldous-Hoover generalization and the one of Lovar-Jaegedi as particular cases. Okay?
It's funny because if you look at, it reminds me, this problem of minimizing a symmetric polynomial.
Yeah.
It goes the reverse direction. They say that this, it's called the Timofte half-degree principle. They say that if you have a symmetric polynomial of degree d, I think, then the optimal solution, if you want to minimize this polynomial, then instead of looking at x to d variables, there will be only, or n variables, there will be d0, only d coordinate that will be different from 0, the other one will be 0. So this way you go the other way around. So you have some x variable with your solution, and you extend by 0 to say that it's feasible solution of your higher dimensional problem.
I see. I want to understand that.
It's called the half-degree principle.
Half-degree principle? Okay.
Timofte.
Okay. I'll follow.
For symmetric polynomial.
For symmetric.
It's a very restricted case.
Okay.
I have
Yes.
another question. So this duplication or zero padding, isn't it just a consequence of the group action, or is it something separate?
It's something distinct. So you could have, I'm showing you a bigger picture. Well, sorry. Whoops, I went all the way to the end. I don't know how to use this thing. Sorry. Okay. So for the nth problem, you have a suitable action of the permutation group on the nth vector space. But then how these are related across dimension, how Vn embeds into Vn plus 1, and how the group action is compatible with that embedding is really key. So although these can be the same, the way a permutation on n letters is expressed as a permutation on n plus 1 or kn letters really depends on how the underlying sequence of vector spaces is embedded inside each other. So yes, for each n, it's the usual action, but how they're related across dimension really changes whether you do duplication versus zero padding or some other embedding. Yeah. Okay, good. So we had this, and then we had for problems related across dimension by duplication, the adjoint of zero padding provides the right notion of projects, and we have this. Let's consider problems related across dimension by zero padding. So the opposite. It turns out that you can write down a similar characterization of the limiting optimal value, but where projects now is the adjoint of duplication. So duplication and zero padding swap roles. Truncating this yields lower bounds via finite dimensional pops. But the relations across dimensions are different because here the relation is un to un plus 1 because they're related by zero padding. And it's the lower bounds because they're related by duplication that go from n to kn. So that indexing, the post-set indexing, if you will, more formally switches. And here we have this rate. And both these rates, 1 over n in the previous slide and 1 over square root of n, are tight, and that we have examples exhibiting these rates. And it turns out that for this theorem, our proof relies on a new dual Finetti theorem that Eitan proved, where you have sequences of random vectors of growing length. If you take the nkth element in the sequence, that random vector, and you sum up k entries successively to get this length n random vector, that this is equal in distribution to the nth element of your sequence. So when you have sequences of random vectors related across dimension in this way, you need a new dual kind of Finetti theorem that characterizes this kind of projection and gives you this reformulation. So that really is the engine underlying the proof of this theorem. Okay. All right, so a couple of illustrations in the last few minutes that I have. with the monomial means problem. This is something that we studied in detail, right? But this is the problem that we had right at the beginning. Bless you. You can simply turn a crank. Everything about our procedure is constructive, sort of fully automated. It's entirely a crank. You can take this sequence of any dimensional problems. These are related across dimension by duplication. You get this sequence of lower bounds where these are sort of symmetrized in that way in terms indexed by partitions of n. And for this problem, you get lower bounds that are like this, and they converge to u infinity of 0, which is what u infinity is here. And they converge at a rate of 1 over n. Right, so each Vn is less than or equal to 0, it produces a lower bound, and it converges at the predicted rate of 1 over n. Graph homomorphisms, yes?
That was a bit
Please.
fast. Where is the finite dimensional pop?
This is the finite dimensional pop. So UNs are the original problems. I produce VNs that are lower bounds, and this is a finite dimensional pop.
Well,
For any fixed n.
For each fixed n, yes.
for each fixed n.
Yes. But each fixed n yields a lower bound.
Yes. But the representation stability property that you mentioned,
Yes.
you mentioned this finite dimensional vector space.
For this sequence of objective polynomials, yes. So the sequence of objectives for the original UNs form a finite dimensional vector space, so I can describe them via finite parameterization to you. But then you turn this crank of rep stability, the Finetti, and so forth, and you get for each n lower bounds of this type. The only reason we stuck with using the same indexing n is because the feasible set here and here is the same, and we can relate un and vn and give you concrete rates. But for each n here, you have this finite-sized pop that gives you a lower bound. You do allude to something that's, I'm not getting into detail here, which is that the sequence of lower bounding problems are also related across dimension in interesting ways, but you can just pick any one of them and get a lower bound.
But in particular, this does not certify, obviously, that U infinity is.
Yes, this does not certify. In general, you should not expect it to because of decidability issues, right? But you will get a lower bound. Right? So this is just a crank, and that gives you this. And Joel's point was that you don't certify that U infinity is non-negative using this technology, and in general you shouldn't, because these problems can be undecidable. Let's look at graph homomorphism densities. If you have a collection of scalars, a linear expression in these graph homomorphisms, if you want to minimize this over all graphs on n nodes, that gives you the nth problem. These are related across dimension by duplication, in that if you take the product of any of these graphs with the k clique, you get a feasible point for the k-nth problem. You turn our crank. The version of the Finetti that's applied is the Aldous-Hoover one, and you get this sequence of lower bounds, where you simply have replaced t by t-ing. T-ing is the injective analog of t, where rather than looking for fractions of mappings between the vertex sets that are homomorphisms, you simply say injective homomorphisms. And so what you obtain, for each n, these are finite-sized pops, and you obtain this rate. Then on the upper bound side, because they're related across dimension by duplication, the lower bounds, the inequalities go with this factor of k. And on the lower bound side, you get with just n to n plus 1, because these are related by zero padding. Now what's interesting here is that there's been a flurry of recent results saying that this problem is undecidable. So U infinity, checking whether it's not negative or not, is undecidable for general HIs. But if you replace t by t-ing and look at the nth problem, that's a finite-sized pop. And certainly that is decidable, and that gives me, so if I replace t by t inch, and I want a lower bound on v infinity instead of u infinity, I can just pick any of these n's and get you a lower bound there. And so the t problem is undecidable in general, but the t inch problem ends up being decidable for reasons having to do with this transformation via d Finetti. The rates are given by 1 over n.
So how is that not a contradiction then?
I'm just saying that I can certify a lower bound on v infinity, and in a decidable fashion.
It's equal to u infinity.
That's true, but
the undecidable thing is for any n.
Yes, that's right.
Okay,
That's
okay,
right.
okay.
That's right. Yes. It was also classically known, by the way, that t and t inch for a fixed graph h, if I fix one of the hi's, there is a relation of 1 over n between them for a graph g of size n. But here we're able to say that un and vn, these optimal values, are related up to a factor of 1 over n based on this general d Finetti crank. Okay? Finally, symmetric functions. This looks insane. There's no 1 over n there. That's the distinction between this and the monomial means problem. The reason we picked this is because these polynomials are all non-negative, but they're not sums of squares for n bigger than or equal to 4. It's a recent example from the literature. You can turn our crank. These problems are related across dimension by zero padding. And so you get a sequence of lower bounds that are related by duplication. And you get, this looks scary, but it's entirely cranky. And you get the sequence of lower bounds that seems to approach 0 numerically. So these are finite-sized pops that we're able to throw the kitchen sink of optimization at and get numbers. And these numbers give you certificates that u infinity is bigger than or equal to this, for example. Okay? All right. A brief word, finally, about STP relaxation. So far, I've just taken an any-dimensional pop and written out a finite-sized pop. Our lower bounds are given in one of these fashions, depending on what the original problem looks like. And each Vn is given by a finite-dimensional group invariant pop, as was alluded to or mentioned several times during the talk. If you take feasible points of any of these lower bounding problems, those feasible points are really any dimensional non-negative polynomials. They're non-negative polynomials or certificates of non-negativity that hold across dimension on the upper bounding side, because they actually provide a lower bound on u infinity. If you further take STP relaxations of these lower bounding problems, you get any dimensional SOS certificates. And so you can couple the d Finetti crank that got us to any dimensional certificates of non-negativity with the sums of squares and moments crank and get any dimensional SOS certificates. And you can state some interesting results. One, for example, is that when you take these SOS relaxations and you fix the degree, so take a degree d SOS relaxation for this problem and this, it turns out that these relaxations are all of the same size. So they don't grow in dimension as n on the lower bounding side increases because of the underlying invariance in relation across dimension. So even though the Vn problem is smaller in size than the n plus 1 problem, when you take SOS relaxations at a fixed level in the hierarchy, you get that these are all images of sections of the same cone. And so these SOS relaxations actually stabilize in size. This phenomenon has been observed in bespoke cases before. And so what we've done unifies and generalizes a number of results. It also provides a rep stability view on this notion of flag algebras in extremal combinatorics. But okay, I'll conclude now. We developed a framework for any dimensional pops where we produce relaxations or bounds using finite-sized pops. And rep stability and D Finetti's theorem and its generalizations play a key role. There are other things that Eitan's been working on. where you can do sort of learning analogs of these things. You can train in low dimensions and apply the learned decision rules in high dimensions if you have a suitable notion of relation across dimensions. Problems where you have sequences of optimization problems or situations where you have sequences of optimization problems of growing dimension also arise commonly in information theory, where the number of channel uses, for example, is a common index in those cases. And so many of the same ideas end up playing a role in giving finite-sized characterizations of channel capacity. And we're interested in several future directions. Thank you.